Hey guys, and welcome back to this video series that we've been making on series and parallel circuits and basically introduction to Ohm's law into these circuits. I'm going to work this problem next, and what makes this problem unique is it kind of takes into account both series and parallel at the same time, and I'll show you what I mean. You see, what happens here is when the current leaves this battery, so think about we have a current leaves this battery, and here comes that current, and that current flows through this 10 ohm resistor. All right, well, keep on going. The current's going to leave the 10 ohm, just like water in a pipe. And then when the current gets to this, and if you've forgotten, we call that a junction. When it gets to that junction, the current is actually going to split. And so part of our electricity, part of our current will flow through, in this case, the 20 ohm resistor. And part of our current will go through the 30 ohm resistor. So typically a problem like this would probably want you to find, say for example, I1, let's call this I2, and let's call this one I3. It would typically want you to find those. Now, here's the thing. This problem has both elements of series and parallel, because you see the 20 and the 30 are parallel because there's a junction. Right before you get to those, there's a junction, and so that current is dividing between the 20 and the 30. But now the 20 and the 30 themselves are in a series with I1. So, because look at what happens. The current going through I1 is going to split. So, we could say something along the lines of saying that I1 is equal to I2 plus I3. Say, for example, if there was 4 amps going into this junction, we know that 4 amps would be divided between those other two resistors. By the way, this is actually the foundation for Kirchhoff's rules, and so we'll talk about those in the next video. But so this is not hard to understand. So here's the deal. Even though this problem looks like it's going to be a little harder, this problem is really not any harder than anything else we've done. My first thing that I want to do is find R total for the circuit. So before I can find R total for the circuit, I'm going to redraw this for a second, because essentially this is what you've got. You've got a 10 ohm resistor, and that's an oops there. You've got a 10 ohm resistor, and it's in series with these other two resistors. I do not want an updated version of Java. Go away. So we've got this 10 ohm resistor. That's the worst ohm I've ever drew. I apologize to every Greek person out there for that. And then we've got this 30 and this 20 ohm resistor as well. And I've got to redraw that because it's just breaking my heart. So here's what you do. You simplify this circuit. First thing is take care of this 20 and this 30. So in order to do that, remember, how do we simplify parallel resistors? We use the 1 over R total equation. So this would be 1 over 20 plus 1 over 30 ohms. And so we'll solve that for R total. And if you forgot how, we can do our calculator. We could do this one without. But 1 over 20, in my case, 11 over 20. Let's see if I can fix that in my calculator. Technology. 1 over 20 plus 1 over 30, right? And then the thing you've got to remember is take a reciprocal of that. Which reciprocal of 1 over 12 is just 12. So that makes for rather easy math, right? So here's the thing. See, these two resistors together have a combined resistance of 12 ohms. Now, what that effectively means is this. We could actually redraw this circuit with the 10 and those other two, and we could replace that with an equivalent resistance of 12 ohms. And now look at the problem that you've got. It looks just like those very first easiest questions that you've seen before. So we've got a 6-volt resistor there. So what's your R total for the circuit? Well, remember, in a series, all you have to do is combine or add together. So this R total for this circuit is nothing but what? 22 ohms. So now, if you remember, we said that was always my first goal with every problem, was finding R total. And then my second goal was always trying to find the I total. Well, just like before, the only formula we'll use for the remainder of this problem is just Ohm's law. As soon as I can get my thing to expand a little here, we know that the potential was 6 volts. So what is the total current leaving this battery? So we'll go back to our Casio again. 6 divided by 22 and 0.27 amps. So we've got 0.27 amps of current leaving the battery. So now let's go through something. You should be able to do most of this problem without me. That means leaving the battery, back at the very beginning of the problem, we have 0.27 amps of current leaving the battery. So what is I1 equal to? Well, follow the electricity. It doesn't branch, so that means it still must have 0.27 amps when it flows through there. So what if we wanted to find the potential? Let's say we wanted to find a potential V1 around that resistor. All we would have to do to find potential at this spot is I times R. There's I, there's R. We multiply it and we'd have 2.7. So that's easy enough. But now we have to go somewhere else. We know that going into this junction, there was 0.27 amps. Now what happens in this junction is that is split between the two resistors that we find here. So we need to talk about how to actually find what this I2 and I3 is. And to do that, I'm going to look back at this problem down here that we wrote again. Matter of fact, just to really make it clear, I may actually redraw that one again, and I hate to waste your time doing that. But then again, I also hate that my stupid tablet is malfunctioning on me. All right. So we were looking a second ago, and we had this basic circuit that we had a resistor, and then we've got these other two split like this, right? And what we talked about is that we knew going into that junction there was what? 0.27 amps going into that junction. We know that those two resistors had a combined resistance of 12 ohms. Well, that means that going through this 12 ohms is what? 0.27 amps. Guess what having this 0.27 amps and this 12 ohms allows us to do? It lets us find the potential across this entire section. So I know that V is equal to I times R. So in this case, I know that I is 0.27 amps. I know that my resistance is 12 ohms. So what is 0.27 times 12? Or in this case, 112. Glad I caught that. And so we've got 3.27 volts. Now, why was it important for me to find the potential? Let's go all the way back up to this initial picture, because now you'll see how easy it is. You see, now I know that around this section, I know the potential on this section is 3.27. These are parallel, and if you remember in parallel, the potential is the same across parallel resistors. So I know that in this problem, I'm going to change my color yet again. I wonder how many color changes I can make in this video. I know there's 3.27 volts of potential on the 20 ohm and there's 3.27 volts on the 30 ohm. And so what that would allow me to do is essentially do this. If I want to find I3, I know V is equal to IR, right? So all I would have to do is grab my calculator, and we would know that the V is 3.27 divided by an R of 30. And so that's 0.109 amps. So there's I3. And then likewise, if I wanted to find I2, the voltage is again 3.27 divided by 20, 0.1635 amps is I2. Now check this out. Let's kind of verify all our work. 0.1635 plus this 0.109. 0.2725, and I guess the one thing I forgot at the beginning, that current was actually 2727 repeating. So we verified that this I2 and I3 both add up to the current going into. But again, the foundation, the part that you have to do is recognize once you find your total current, that's the current going through this section. So you use that current and you use the resistance of this section to find the potential. Because once you know the potential of the section, that potential is the same across each of the resistors. Even if we had 5 resistors, all we would have to do is find the current going through the 5 resistors, multiply that current times the resistance of the combined 5 resistors. We would then know the potential across all 5 of the resistors. Anyway, I may do another example of this, but hopefully you've kind of got the grasp on it. So do